Section 2.4.1 Free damped oscillation.
So we've got a mass spring damper system, MSD system. You'll come across this loads and loads and loads of times because this is now a real system, okay? We've got a damper and a spring. And so if I started that oscillating, what do you think will happen after a certain amount of time? It's going to stop, yeah? And the reason it stops is that we're taking out energy using the damper, okay? And so as time goes to infinity with this system, what happens to the amplitude? It goes to 0, okay? So if we start looking at Newton's second law, mass times acceleration equals the sum of the forces. Well, I've got two forces, they're both opposing. I've got my damping force, Cx dot, and I've got my spring force, Kx. Okay? They're both opposing, hence the minus signs. And I can move them both to one side and end up with this equation, which again is one of the fundamental equations in all of physics. And you'll see this in the first lecture of the control series, okay? Because it's often talking about mass spring damper systems. Mx double dot plus Cx dot plus Kx equals 0. And you'll see that again and again in this course as well, okay? Often we'll have an F at the other end, but instead of a 0, but you know, that's by the by. And we're going to set some shorthand notations, okay? Omega naught squared is K upon M. That we saw before. But this new one, gamma, okay, is C upon M. So if I take that equation, that one there, and if I divide both sides by M, I end up with C upon M and K upon M. And obviously K upon M is omega naught squared, sorry, and C upon M we've just defined as gamma. Oops, computer. So the equation of motion could be written like that. Now the challenge is to find the solution of x of t. X is a function of time. And we can make the prediction that the system will oscillate at a frequency at or less than the natural frequency. Now if you think about it, if damping is low, really low, okay, and you let the system oscillate, it's going to go backwards and forwards, and the frequency of that oscillation is going to be omega naught, okay, because there's no damping. But as you increase the damping will slow the motion down, yeah, because it's responsible for taking energy out of the system, and that the amount of force that's being applied is proportional to the velocity. So it's going to slow it down, okay? And so what do you think happens to the frequency? Okay, yeah, it decreases, it goes down. The frequency will slow down, okay? So we can make a prediction that omega, the frequency at which the system is going to oscillate is going to be at or less than omega naught, okay, with a damper. And this is an example where the complex plane will help solving this problem. We're actually going to use it in a couple of places. So we're going to move to the complex plane. We're going to replace x with a complex number, okay? And I've called that complex number z, okay? So we've just stuck z in where we had x, okay? And the trial function now, we know that z is a complex number, so we're going to try the fact that it's going to oscillate, okay? Now I've got p, t and alpha in here. Let's not worry too much about it, but remember the p, you know, with that form of that equation, p smells a bit like a frequency, yeah? It's, you know, we had j omega t plus some phase angle. So alpha is a bit like a phase angle, p is a bit like a frequency, okay? They're not just at the moment, but let's just think about that. We're going to try that as a trial function because we know the system is going to oscillate, but we don't know at what frequency, and we don't know where it's going to start in terms of the equation. So that we can apply this as a trial function. And so we take derivatives. So obviously the first derivative, you get a jp coming out. Okay, j times p times t. The alpha, obviously the derivative of a constant is 0, so that disappears. So that's jpz because that's z. So you end up with jpz. Second derivative, obviously you get another jp coming out. J squared is minus 1, hence the minus sign, and p squared is obviously p squared. And so the second derivative is minus p squared times by z. Let's stick that back in the equation. So there we are. So we've stuck in, for z double dot, we've stuck in minus p squared. Okay. For z dot, we stick in jp times by gamma, because obviously we've got gamma up there. And here we've got omega naught squared times by z, Okay, so you've got that in there. That's what we had before. Now the only way this equation can be solved is if we make p a complex number. Okay, so we're using it again. P is a complex number. If you think about this equation up here, okay, the only way that we could solve this equation is this: either z is 0 or z is our oscillation. That can't be 0, okay, so that can't be 0. Therefore this lot must be 0. And if you've got a complex number, which that term is, okay, we've got two real bits and a complex bit. For a complex number to be 0, the real bit needs to be 0 and the complex bit needs to be 0. And the thing is, p can't be 0 because that's a frequency, like I said, it's not like a frequency. Omega 0 can't be 0 because that's our frequency of oscillation. And gamma can't be 0 because that's no gamma. I mean, damping is not there. Damping is there, okay? So that term can't be 0. Therefore, we've got a solution here that we can't seem to solve. But if you make p a complex number, we can solve it. And so that's what we've done. P equals n plus js. Again, n and s, they're just terms we're using. They'll disappear in a minute. So we make the substitution in there. So obviously p squared is n squared plus minus s squared plus 2jns, okay? So we can stick that in for p squared, and obviously the minus sign in front of the s term, this one, is because j squared is minus 1. Okay? So we can stick that into where p squared is, and obviously we can stick in for p, we can stick in n plus js. So end up with this equation on the bottom. Now look at what happens, okay? We've got a real bit, a real bit, and a real bit, and a real bit. That can be equal to 0. And this odd bit as well, can be also equal to 0, depending on what certain things are. So if we move through, real parts must sum to 0, imaginary parts must sum to 0. So if you take the real bits, okay, s must be equal, sorry, the imaginary bits, s must be equal to gamma minus 2, gamma upon 2. Take this equation, set it equal to 0, you get a value for s. And if you do the same thing for this bit, obviously here we can substitute in for s with gamma upon 2, so that's why we've got gamma squared upon 4, gamma squared upon 2 in there. N squared must be omega naught squared minus gamma squared upon 4. So we've got two terms which combine to make p. And so if we remember we had z equals a pt plus alpha. Well, we stick in for p nt plus j, n plus js, and so you get nt plus jst. Obviously, with an exponential, you can separate it out. So we've got a e to the j times jst, and then e to the j nt plus alpha. This, like I said, looks like that. The real part of that is an oscillation, isn't it? Yeah. Where this turns into minus gamma upon 2 times by t. Now that, notice we've got the multiplication of two
exponential parts.
Okay. One of them is an oscillation, this one here. Yeah, that looks like an oscillation. We all agree? That's what we just covered in compensation. This one, what's going to happen as t goes up? T is 0, what's the e to the 0? 1, okay? As t goes up, what happens to that term? It goes down. There's a minus sign here. It's a decaying exponential. Okay. So like I said, e to the minus gamma upon 2 times by t is a decaying exponential. And e times j times something we know is an oscillation with a frequency of n in this case. Now n is a frequency and it's known as the damped natural frequency. Okay? And that is a frequency at which the damped system will oscillate. And that frequency depends upon your damping in the system. Okay? It's dependent upon gamma, which is C upon M. And obviously C is your damping. And so if we stick in, we had up there, we've got nt plus alpha. Okay, we've got gamma upon 2. So you stick in n equals omega d, you get an omega d in there. Okay, and so here we've got our equation for z. The real part of z, so obviously the e j omega t stuff moves to cosine j omega t, and so you end up with our solution. A e to the gamma upon 2 times by t times by our oscillation of frequency omega d. Okay, that's an amplitude. There's no issue with that. This bit is our oscillation, okay, and the frequency of oscillation is omega d, a damped natural frequency. This bit here is the new bit, and that's causing it to decay, the amplitude of decay, to 0 as time goes up. So you can see quite clearly that, x of 0, the starting off time, you're going to end up with a times by 1, because that's 0, so that term becomes 1, a cosine omega t, so it's going to start oscillating. You pull it back, a mass spring damper system, you put it back, let it go, it's going to start oscillating, okay? But obviously as t goes up, that oscillation is going to reduce in amplitude with respect to this term. And as t goes to infinity, so eventually, okay, that term is going to be 0, so the oscillation stops. Okay, that's the solution for a damped system, mass spring damper system. Okay. So if we plot that, we end up with this situation. Okay. So like I said, here's my equilibrium position. I pull the thing back, or I lift it up, or whatever, by a certain amplitude, and I let go. And depending on damping, we end up with an oscillation that decays with respect to time over and over and over. Okay. Here I've listed x1 as my amplitude A, x2 is the second peak, x3 is the third peak, and x4 is the fourth peak, and so on. And there's a relationship known as the logarithmic decrement that dictates how quickly the system will decay in terms of time. Again, that is related to how much damping you've got.